I'll be covering now lecture 18, the complementary principle of virtual work, which is different and is also called the principle of virtual forces. And in this case now, is a little bit different from the principle of virtual work. When we cover the principle of virtual work, the displacement field was varied while keeping external forces fixed. In this particular problem, what we're going to do now is to take the tractions and body forces and vary them while keeping the displacement field fixed, which is a little bit different. So in the complementary, virtual work, will vary the tractions and body forces and keep displacements fixed. So in this situation, we will demonstrate that external complementary virtual external work is equal to the complementary internal virtual work. And we will demonstrate this is correct, that this is going to occur. So let's start with external virtual work, the complementary version, double integral, and we'll vary tractions now. We've been varying all along deflections. We'll be varying tractions now instead, because we can. And we will show now that we can substitute Cauchy's relationship. So we can substitute relationship, which states that Ti of n equals sigma ij nj. So I get this. And now I'll use Gauss theorem to convert the surface integral to a volume integral. And that simply becomes ui sigma ij comma j d volume now. And now I can expand this and get ui comma j sigma ij plus ui sigma ij comma j. And I do have a mistake in the sense that there's a variation here. So let me add that there, variation there, and variation here. I should clean it up so it's clean. I apologize. We'll just do it quickly here and patiently. Okay, so that's what this expression is. And I'll collect terms now. in this way. And notice how this, the del can be factored like this, but this is zero due to equilibrium. And so now I'm left that external virtual work, complementary version, is equal to this expression. But we know how to deal with that. We know that ui comma j, del sigma j can also be written as epsilon ij plus omega ij del sigma ij. And we already know that this is a strain, infinitesimal strain, this is a rotation tensor, and that we already know what's going to happen here is that this term does not work, virtual work, because this is a skew symmetric tensor right here, and that's a symmetric tensor right here, and the multiplication of a symmetric tensor times a skew symmetric tensor gives you zero. We've already demonstrated that. So therefore, what I really have is the external virtual work is equal to the internal virtual work. And I just demonstrated to you that's the triple integral volume epsilon ij del sigma ij dv. So I've demonstrated that, and we've got into that conclusion. So now what I want to do is to derive the Euler-Lagrange equations implied by the complementary principal of virtual work. And to do that, I'll start with the fact that I already know that the complementary internal virtual work equals the complementary external virtual work. And I will write everything on one side of the equation if that's okay. So I'll do this minus equals zero like that. And I'll start over. Integral volume epsilon ij del sigma ij dv minus volume ui del bi dv minus, and then this on surface 1 ui, and I could be specifying a deflection, so let's make a ui bar del ti and ds equals 0. And so what I'll do now, and bi is the body forces, let me remind you, ti are the tractions, ui are the deflections. Okay. So we know how to approach it. We'll substitute the fact that bi is equal to minus sigma ij comma j from equilibrium. We know that. And in addition to that, we know from Cauchy's relationship that Ti is equal to sigma j and j. We know that. So we get the following expression. And the sign is became positive. And I have minus like this. Again, I'm substituting Cauchy's relationship here, and I'm getting closer. So now let's integrate by parts to remove this comma j. And to convert this into a volume integral. So if we integrate our parts, we get the following. I'm going to integrate our parts, this term here. So let's do it here. So I get the minus, and that goes inside the volume. Perfect. And now I have plus the integral over omega 1 ui nj del sigma j plus integral omega 2 e ui nj sigma j, like that. And I forgot the surface ds there, minus ui bar nj del sigma j ds equals 0. I apologize for that. Everything got cramped in there for a second. So move this arrow like that so everything's cleaner. I want to focus on this term a little bit more moving forward. We've already taught that ui comma j del sigma ij is equal to epsilon ij plus omega ij del sigma ij, and that I get epsilon ij del sigma ij plus omega ij del sigma ij, and the rotation tensor times the symmetric tensor, that'll give you 0. So because this is skew-symmetric and this is symmetric, so I get epsilon ij I apologize for that. Let me move here. Right. And epsilon ij is 1/2 ui comma j plus uj comma I. So del sigma ij. So this is equal to that. We know that. So I'll substitute that here. I'll substitute it into this expression here. And I get the integral of epsilon ij del sigma ij dv. And then I also get minus 1/2 ui comma j. I apologize for that. It's a glitch. And then I have all these other terms that need to be looked at. Sorry about this. All these terms. Now, you can see here that if I were to specify, like this right here is del ti. And this right here is del ti. And this right here is del ti. if I specify tractions on this partial omega 2 boundary, this goes to 0 if Ti is specified on omega 2. And you can see how now things are starting to simplify. And now I can apply fundamental lemma of calculus of variations. And for any del sigma ij, then I have that epsilon ij must be equal to 1/2 ui comma j plus uj comma I. That's the Euler-Lagrange equation in V. Secondly, I have that you also have that this is equal to that on the boundary. And then that comes out automatically. Ui equals Ui bar on the boundary. We also specified tractions on the boundary. In other words, the complementary principal virtual work, the Euler-Lagrange equations turn out to be the kinematic relationships. And I went through all of this, but in reality, I didn't have to. It looks like I tricked you, but for example, I could have just gone straight to this. I could have written this so it looks more clear. I could have written this as 1/2 ui comma j plus uj comma I, like that. And I know this is omega ij, and omega ij times this is 0, so I will have gotten this. And that way I'm not using the strain deflection relationship because it looks like I did. And so when I got to this step and this step, this came out automatically. I didn't force it. It just came out automatically. So it's impressive how I derived the kinematic relationship, the kinematic relationships of strain to deflections without even using it. And that is quite powerful here. Using the similar arguments I discussed in the previous lecture, we talked about the theorem of total potential energy. I can also derive the complementary theorem of total potential energy. Applies for conservative deformation system, and it applies for elastic, well, this is elastic material, and conservative I apologize for that. Forces. And so if that is the case, then we can say that if I calculate, determine the complementary strain energy, U star, and we want to determine the complementary potential energy due to laws applied, then what I'll get is that the first version of pi star is equal to 0. And here, pi star, and then pi star here is going to be where pi star is a function of stress now. So that's these are my functionals now, my functions now, and is going to be equal to U star plus V star. And the strain energy density, the strain energy density for small U star is going to be equal to for linear elastic material, sorry about that, is going to be 1/2, and that's going to be Sijkl sigma ij sigma kl. Now you want pi to be in terms of stress. And Sijkl is the inverse of this one. And so, yeah, so this is how you approach the problem. Here, V star is really the minus of Tin Ui ds, just like before, minus over the volume Bi Ui dV. So that does not change. The only thing that's changing now is that pi has to be written in terms of sigma ij, and U star is 1/2 of that for linear elastic material. Okay. Conversely, you can find U star by taking the integral 0 to sigma ij epsilon ij d sigma ij. In other words, you're finding the area under the curve, but now respect to the strain. And so now this big U star becomes the integral of small U star dV plus V star, which is given here. So I hope that makes sense. We'll now start moving to a new topic. So hopefully this makes sense. Again, the principle of virtual work gives you the Euler-Lagrange equations, and the Euler-Lagrange equations are the equations of equilibrium, while the complementary principle of virtual work gives you the Euler-Lagrange equations as the strain deflection relationships, which is quite incredible because I didn't use the lecture on kinematics. I was able to find that through the virtual work principle. And then I specialized the virtual work principle for complementary version for conservative differential process, conservative forces, and demonstrated that now this relationship also holds. And so what the theorem is really saying, to go to the theorem now, in this case, is telling us, so what the theorem is saying is, and that's the theorem of total complementary energy. What the theorem is saying now is of all statically admissible stress fields the stress field which corresponds to kinematically admissible displacements makes the total complementary energy stationary. So we've shown that that is the case, and this is what we mean with stationarity, and that's the complementary version of the theorem of total potential energy. So with this, we conclude this lecture, and we'll pick it up in the next lecture.